my channel, and today I'm going to be talking about the history of physics. This video specifically, I'm going to be talking about the general theory of relativity. General Relativity was published in the year 1915 by one of the most influential scientists of the 20th century, namely Albert Einstein. So let's begin by talking about what is general relativity. General relativity is a theory proposed by Albert Einstein that rewrites the Newtonian version of gravity. General relativity is a more accurate description of our universe itself, and general relativity describes all and most of the phenomena in our universe. So to truly understand general relativity, we must talk about the Newtonian version of gravity first. So what is the Newtonian version of gravity? Newtonian version of gravity. So we have the Newtonian version of gravity. So we first have to talk about the inverse square law, which states that we have F is equal to G times M1 times M2 all over R squared. Okay. So this is the inverse square law over here. F is equal to G times M1 times M2 all over R squared. Now let's talk about an example of Newtonian gravity. So we have the first scenario, which states that if we have on planet Earth a tree, an apple falls from this tree, this is caused by gravity, and the same force states that when we have the sun and planets orbit around the sun, this is also caused by gravity. And this is the second scenario. So as you can see, we have two scenarios over here that depict gravity itself. Now, this is a pretty okay description of gravity. But the thing is, we have to look at the equation itself over here. So we have F is equal to G times M1 times M2 all over R squared. So the force is equal to the G, which is a constant, times both masses, M1 and M2, all over R squared, which is the distance between the centers squared. Now, most people think, okay, this equation is pretty precise, and yes, of course, there's nothing wrong with it. Well, the thing is, people saw, well, specifically Einstein, he saw that why should we consider gravity as a force? And Einstein didn't perceive gravity as a force. Instead, Einstein thought that gravity is just a curvature or a bend in the space-time continuum, which is very odd because right now we all learn in school the Newtonian version of gravity. The gravity is a force, and that we have two objects that exert a specific force on each other, and so on and so forth. So we think of gravity as a force, but in reality, gravity is not a force. This is the main difference between the Newtonian version of gravity and Einstein's theory of relativity. Einstein specifically denied the fact that gravity is a force. Okay, now let's talk about Einstein's version of gravity. Einstein's version of gravity. So we have Einstein's version of gravity here. Now, to understand Einstein's version of gravity, we need to talk about space-time continuum. So to understand that, we need to talk about space and time. So space is essentially just a three-dimensional system. Why is it considered a three-dimensional system? Well, one, we're three-dimensional, and two, we can essentially describe the position of any object using three coordinates, x, y, and z. On Earth, we could say longitude, latitude, and altitude. Okay, so that is pretty okay because we have space, and we'll just call it a three-dimensional system. Well, what about time? Time we can consider a one-dimensional system. So for years and decades, and centuries maybe, people have been considering that time and space are not one. They're considering that time is different and space is different. But Einstein, and specifically Hermann Minkowski, Hermann and Minkowski combined space-time, and Hermann and Minkowski was Einstein's one of his professor. So Einstein and Minkowski stated that, what if we combine space-time? And he stated that space-time is a 4-dimensional system, because we have 3-dimensional system and 1-dimensional system. But why do we have the need to combine space and time together to make a 4-dimensional system? Well, one, it has very much of a practical use. So for example, if we take this pen over here, and we just throw in this pen, like this. Okay. Now as you can see, my instincts show that it's just going to curve up and come over here, and so on and so forth. That's instincts. But in mathematics, we can describe the motion too. We know the exact force and the exact speed that my hand throws it off. Of course, we can use classical mechanics to describe it. However, we can't really describe the motion of this object when considering the time unit. Why? Well, if we throw this object over here, over here, over here, this object goes like this. So as you can see, if we trace it out over here, this object goes like this. Let's trace it out, it goes like this. This is the path of this pen over here. Now, if we describe the position of the pen when it's over here, so if the pen is over here, it's going like this. If the pen is over here, we can describe it with x, y, z. But we can't really describe it because, say, the position of the pen goes exactly the same way. And we have x, y, z over here too. X, y, z. Then we essentially just have two of the same coordinates. So which one are you referring to? Well, the thing is, we're referring particularly this one over here. So we have to add a time component. So when we add a time component, we have 4 coordinates, which in turn creates particularly a 4-dimensional system. Now this is one of the basics of special and general relativity. So to understand them, we have to talk about abstract things like space and time. Okay, now that we've talked about what space-time is, let's talk about the 4-dimensional space-time continuum, because we have 3 dimensions and 1 dimension. So the 4-dimensional space-time continuum. So to think about it, even mathematicians, the people who are really dedicated to mathematics and topology and other branches of mathematics, when we consider topology, for example, topology is studying objects like 1 dimension, 2 dimensions, 3 dimensions, 4 dimensions, and etc. So topology is study of objects and how we can morph them, morphism, and so on and so forth. So that's what topology is considering. Topology is considering how we can morph objects. But sometimes in topology we have extra dimensions too, like 11 dimensions, like 5 dimensions, or like 4 dimensions, and so on and so forth. As humans, we cannot perceive 4 dimensions or anything more than 3 dimensions. So we cannot perceive that because we aren't really in 4 dimensions, and our minds cannot just handle that type of thinking. Okay, so we're drawing this 4-dimensional space-time continuum on a 2-dimensional plane. So this is essentially a 2-dimensional space-time continuum. Let's just draw lattice points over here, as it is commonly drawn. So kind of like a mini coordinate system. And as you can see, we have the space-time continuum over here. Now, you may be wondering, we have a space-time continuum, then how does gravity have an intricate relationship with this space-time continuum? And that's the main question. Well, gravity does have a very significant relationship with the space-time continuum. To describe it, let's just say we use green, for example, and we'll call this planet P. Planet P. It's in green. So if we describe planet P, and we put it on a space-time continuum, which will say that a space-time fabric. So we have a space-time fabric, and we hold it on the sides. And then we put an object. Of course, the space-time fabric curves. We have a bend in it. So we have curvature. And as you can see, curvature just kind of changes to space-time itself. Because if we just have regular space-time, no objects, we put a mass in it, which we have an object, it curves. Now if we put another object, it also curves, but instead, and if that object's mass is less, it starts going towards it, if we talk about with friction and stuff. So generally, we can see that with a regular type of fabric. If we think about the universe like that, a regular type of fabric over here, when we put an object here, the space-time around it bends. And this is definitely how Einstein perceives gravity. He thought about the space-time continuum bending, and so on and so forth. So if we have the space-time continuum that's bending, all of these tiny coordinate system like points, over here, over here, over here, they start to bend too. So we have a warped environment. So then we have to talk about a world line. So what is a world line? If we throw an object, the world line is the natural path that an object follows. Now, if we have gravity, for example, gravity can interfere with the world line of an object. It can kind of warp it, because since these coordinate type of system points are warped, because any event can happen on space-time. For example, an event, when I'm 5 years old, that can happen on space-time too, because it extends infinitely in both directions. Well, if we consider the Big Bang, it might not have infinitely many things because time started from the Big Bang, but it could consider a finite amount here, and who knows when the universe will end, so we'll just say finite too. Okay, so as you can see, we have a specific space-time continuum for the time of our universe. Now, as you can see, we have any event of our lives on here. Now, as you can see, when we bend this, space bends too. So we take an object, the space around it bends. So which means that when we put an object on it, or another object, for example, a moon or any other thing, the world line of it bends because these type of coordinate systems in a specific time period or in a specific space period also bend. Let's just say they bend like this. Then, if the object is supposed to go like this, it curves, or it just changes according to how the kind of warped coordinate system is. So as you can see, we can have, this is how gravity is perceived by Einstein, and this is how the more accurate representation of gravity is. As you can see, when we have gravity and we throw an object on it, sometimes it orbits around. For example, the moon orbits around the Earth. That's when, if it gets too close and it just orbits around the Earth, there's no friction, which is why it doesn't collapse in, and that's how we call orbits. On the other hand, it could just slightly deviate away. So as you can see, for example, essentially General Relativity perceives gravity as a curvature in space-time. So that's essentially what space-time is. Okay, now that we've talked about space-time and how it's a continuum and how bending it warps the system, and how when we bend it we place other masses on that system, they move, which is what we call gravity, let's talk about a little bit more about how gravity and general relativity, specifically general relativity, is proved. Because the whole thing we're talking about space-time continuum and so on and so forth are all in the fields of general relativity, not the Newtonian version of gravity. By this time, Albert Einstein doesn't even consider gravity to be a force. He calls it general relativity. So general relativity is very important. Now, this is where we come to Arthur Eddington. Arthur Eddington was an astronomer. Now, astronomers are essentially kind of like experimental physicists, except for the fact that they don't have machinery or anything. They just observe the night sky. So usually scientists always depend on the experimental knowledge or the observations of nature to create their equations. They want their equations to be reliable. So if nature behaves differently, they change their equations. Now, how do we prove the general theory of relativity? Well, the general theory of relativity also has a lot of mathematics, differential geometry to be exact, and Riemann geometry. Differential geometry is essentially particularly the calculus of curvature. So for example, when we have space-time, for example, it curves, we could call it differentiation and curvature combined. So differential geometry is a very hard subject, and Albert Einstein used it, and he formulated equations. We also have Einstein's field equations. So we have tons of equations, and when they calculate it, they say this one thing. So if we draw space-time, remember this is not accurate because we're not in 4 dimensions. However, we're drawing it on a 2-dimensional plane, and we have, we'll call this the sun now. And if we have the sun, then we have tiny little stars over here. Now these stars, their light comes straight. But when we have the gravity warps it around such that the light travels to where we are on Earth. It warps. It warps. So the light warps around the sun to essentially just show where the Earth is. So that's one thing that particularly Albert Einstein's equations show. we have the light is warped because of gravity and around the sun, and it goes to the Earth, which is why we can see stars behind the sun. But people didn't believe this. So the astronomer Arthur Eddington decided to test it. So when an eclipse came, they tried to find the stars, and exactly Albert Einstein's equations proved the truth. Exactly, the reason we can see the stars is because their light is warped around the sun. So Albert Einstein's general theory of relativity is proved after Arthur Eddington found it. Okay, now that we've talked about general relativity, space-time, Arthur Eddington, let's talk about determinism. Now, determinism is a pretty easy concept. Think about classical mechanics. In classical mechanics, when we have one thing, we can measure it, the velocity or something, and we know all the initial conditions of an object, we know where it will end up. For sure, that's determinism. However, what if we throw an object and it ends up 75% of the time here, 25% of the time there? Then that would be probability, right? It's a probabilistic approach. So quantum mechanics, which is the rival theory, and it's not compatible with general relativity, takes the probabilistic approach, whereas general relativity takes the deterministic approach, and classical mechanics also takes the deterministic approach. Albert Einstein thought that reality should be in a deterministic way. Even if it's way complicated or if it's way simple, it should always be deterministic. But on the other hand, physicists, and especially quantum mechanicists, they thought that we have to accept nature as its nature. So they thought, okay, it's probability, it's a probabilistic approach. And this is why Einstein didn't like quantum mechanics. So general relativity is a deterministic approach. Now that we've talked about that, let's talk about the applications and more. General relativity is very important because it describes gravity, and we can even use it on planet Earth. For example, we can talk about how the satellite's clocks tick faster or slower depending on Earth. For example, we can use general relativity to compute the difference. And we can use general relativity for theoretical cosmology. Most of cosmology is based on Einstein's field equations, theoretical cosmology to be specific. So Albert Einstein's equations have a lot of applications. Okay, now that we've talked about general relativity, determinism, space-time, Arthur Eddington, applications, and more, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.